All right, so we started our look at what does it mean to have the rate of change. And here is the average rate of change. And if you just remember, the average rate of change is the slope of the secant line. And an example is, well, if we know where our position is over how much time, we can get an average speed. So now let's use our tool of the derivative. Okay, so let's look at this function here. F of x equals x squared plus 3. So 1, 2, 3. Here is x squared plus 3. Alright, so let's say, I want to find the derivative at a point. So let's say over here. Okay? Or I want to find the rate of change at a point. Now we could use the average rate of change. So this would be the secant line. Okay. Or we can use something called the instantaneous rate of change. And that would be the slope of the tangent line. So the interesting thing about the slope of the tangent line is that at this moment here, it gives us the exact rate of change of this function. See, the secant line gave us the average rate of change. This gave us the exact rate of change, and we call that the instantaneous. What is happening at that moment? So the derivative can tell us the rate of change, the rate that the function is changing over x. Okay. So because of that, we say that the derivative of function is the rate of change for that function. So the derivative is the rate of change of the function. Right. So let's go ahead and let's kind of summarize this with a little, I don't want to say a table, but a summary here. Average rate of change. Here's our average rate of change, and then this is going to be the instantaneous. Instantaneous rate of change. So the average rate of change is the slope of the secant line. And the formula we just went over. Average rate change equals f of x sub 2 minus f of x sub 1 all over x sub 2 minus x sub 1. And you have to use that if you have only data points. You don't have a function, but you want to find out, well, get an idea of what is the rate of change. Now the instantaneous rate of change is the slope of the tangent line. And to get that, we say that the rate of change equals f prime of x. Now notice over here we have to write average rate of change. Here we just write rate of change. So if you're ever asked to find the rate of change, it's assumed to be instantaneous. Assumed to be instantaneous. All right. Okay. So let's look at how we're going to use the derivative and the instantaneous rate of change. And one of the most well-known rates of change is that of a velocity. One of the most well-known rates of change is velocity. All right. So, I don't know if you've taken physics or not. If you haven't, that's not a big deal. We go over everything in this class. If you have, you might have a little bit more insight into this. But we use s of t. This is what we use for our position function. And a position function is usually either in feet or meters or something like that. I mean, I guess you could use inches and centimeters, but some length, some distance. And then if we were to take the derivative of this position function, that's going to give us our velocity function. And the velocity function is either going to be in feet per second, meters per second. You can do it over hour or over days. Something where you have you can do it feet per minute, meters per minute. That might be common. But a distance over time is the key. Okay, so you have to remember that if you're given a position function, that the derivative of the position is the velocity. Okay, so to start this off, we're going to look at what's called a free fall problem. Free fall problem. And in a free fall problem, the acceleration on the object is only the Earth's gravity. So the acceleration on an object is the Earth's gravity. All right, so see what we're talking about here. So let's say you're standing on a building. Okay, and you have a ball and you drop it. Okay, at the moment you drop the ball, the only thing acting on that ball is Earth's gravity. Okay. And then, of course, until it hits the ground. Now, for this class, we're going to say that up is positive, down is negative. So the Earth's gravity acts upon an object in the negative direction. The Earth's gravity acts upon an object in the negative direction. Okay, and then the reason I'm saying that is sometime in physics it's the opposite. I'm not sure why, but physics tends to want to say down is positive, but I guess that's just the way it is. Okay, and then finally, let's look at the two equations for position. So there's two equations for position. Okay, so first we have metric. And metric, S of t, is going to be a negative 4.9 t squared plus v sub naught times t plus s sub naught. All right, now v sub naught is our initial velocity. And s sub naught is our initial position. Okay. Now the second version of this, it's, you can either call it English or standard, something like that. And then this is s of t equals a negative 16 t squared plus v sub naught of t plus s sub naught. And so the difference between these two is, in metric it's meters per second, and in English standard it's feet per second. So because there's a difference between meters and feet, we have these two equations, and we'll use both of them. Okay, so again, we have this concept of rate of change, and the rate of change has to do with what is the slope at a certain point. Now if you have to do a slope of a secant line, that's the average rate of change. If you can get the slope of the tangent line, which is usually more preferable, that's the instantaneous rate of change. You can't do this if you don't have a function, so of course that becomes a problem. So if you only have data, then you have to do the average rate of change.